Okay, we got some data, and we want to find a least squares regression line. So let's do that. Let's open our data, and let's open it in StatCrunch. Okay, I've got the number of absences and the final exam score. Let's go to Stat. Let's go to Regression, Simple Linear Regression, and let's pick our X variable and our Y variable. We're going to just compute. We've got everything we need in the options for now. I'm going to make this larger so I can read it. Now, my equation is actually right up here. Y is, but there's no consistency between the problems and StatCrunch in terms of which coefficient goes first. So the negative 2.84 is the coefficient of X. 3 decimal places actually rounds to negative 2.84, only 2 decimal places. So that's that. And then the intercept is the 88.92. So interpret the slope and the y-intercept. So it's like saying for every additional absence, you would expect the person's score to drop by 2.84 points. And if they have 0 absences, they'd get like an 88.92 on average. So this is part C. For every additional absence, the student's final exam score drops by 2.84 points. If they had no absences, they'd be getting 88.92 on average. Predict the final exam score for a student who misses 5 class periods. Well, let's go back to to StatCrunch. Go to Options, Edit. You can put in prediction options down below. Where is it's actually further down? No, where am I? It's prediction of Y. An X value of 5. Predict the final exam score for a student who misses 5 class periods. So I have to scroll down a little bit. It's down below. Predicted value. For 5, we would predict 74.72. That's what you'd predict. Compute the residual. Well, I think we have to look at the data. There must have been somebody who had 5 absences. Oh, here we go. And they got 73.1. That's actually, so we want to find what's the residual for that one. Let's actually let StatCrunch let StatCrunch do the math for us. Under actually back under StatCrunch, I've got my my simple linear regression. Go back to the options and edit the options. If we scroll down, you can ask it to save the residuals. Let's just save the predicted and the residuals. Click compute, and actually let's close that. So for 5 absences, we would predict 74.72. The residual negative 1.62. Let's copy that over. That's the residual that we're talking about. Oop, that's way too many decimal places. Thank you. Is the final exam score above or below average? If the residual is negative, that means it's below average. The actual score was less than what we would have predicted on average. Draw the least squares regression line on the scatter diagram. Well, let's let StatCrunch do that. Let's go back to the hidden simple linear, and it's actually done that for us on the second page. You click on this, and you get your you get this. Now I'm going to edit the y-axis so that it goes from 0 to 100, because that's what all of the options, all like the multiple choice options have. It'll just look a little bit better. It'll be easier to compare. So that's what we've got. Let's see if we can compare it. It's clearly this one. You never get a regression line that's going to go beep 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 beep. There's definitely a downward slope. I don't even know if you needed to do that yourself. It's clearly not in any of these, because the regression line is a straight line that follows the data, and it definitely has a downward slope. So would it be reasonable to use a least squares regression line to predict the final exam score for a student who's missed 15 class periods? Well, It would not. And the reason is our data only includes people who have missed up to 9. So anytime you have something outside the scope of the model, it would be called extrapolation, and it really is not appropriate to use this model to extrapolate. So no, 15 is outside the scope of the model. Analyze the residual plot below. Ooh, let's get analyzing. Let's make it a little bit bigger. Oh, that's not going to scroll for us. Okay. What condition is violated? Well, there's a pattern to the residuals, right? There's a pattern. It's a big curve. There's no outliers per se, because there's not like 1 or 2 values that are like really, really far from the rest, but there's this clear curvy pattern. That's not okay for a residual plot. You should have a big cloud that's like a scatter. Okay, for the data set below, compute these parts. This is some stuff from week 7. This is inference on these parameters. So let's open this in StatCrunch, get our data. We're going to first, under stat, go to regression, simple linear regression. The x variable is here, the y variable is there. We're going to do this standard settings and compute, and let's look at the output that we have. Down below, oh, actually, the parameter estimates is where we're going to be focusing our attention. We've got an estimate for the intercept and an estimate for the slope. This B0 is the intercept estimate. Okay, so that's what we want to copy over, but I have to round it up to negative 3.291 because I need 3 decimal places. That's my intercept is my B0, and B1 is this one. And again, 3 decimal places, I have to do more. I have to do rounding up. 2.128. 2.128. Compute the standard error, the point estimate for sigma. The standard error of my model is given to me right up here. The estimate for the standard error deviation, that's here. And I wanted to get it for with 4 decimal places, so I'm going to take that. But again, rounding up, 0.5534. Let's paste 4. Okay. Assuming the residuals are normally distributed, determine standard error of B1. That's given to us in the table. B1, remember, is the slope estimate. Standard error is right here. Does it want 4 decimal places? No, it wants 3 decimal places. Guys, watch out for that. It keeps changing it from 4 to 3 and so back. 0.133. That's what my estimate for standard error. Assuming the residuals are normally distributed, test the null hypothesis beta 1 equals 0 versus beta 1 not equal to 0. The p-value is given to you in the bottom of the table. It's right here. It's really small. 3 decimal places would round to 0.001. So that's my answer. So this is saying, could the slope possibly be 0? Well, the data suggests not, because it would be extremely unlikely for me to have data like this if the true population slope was 0. So I would reject that null hypothesis and go with the alternative hypothesis, which is the slope is not 0. This is another way of saying that a linear model is appropriate. There definitely is a linear relationship. Make a statement regarding the null hypothesis and draw a conclusion. Do not reject, we do reject null. We're rejecting the null hypothesis because there is sufficient evidence at that significance level that conclude that their linear relationship does really, really exist. That's my conclusion. Okay, the data in the accompanying table represents a rate of return of a certain company stock for 11 months, compared with the rate of return of a certain index of 500 stocks. Both are in percent. Let's look at the table. All right, let's just bring it into StatCrunch. And I'm going to it's asking me for an estimate of beta 0 and beta 1. So it's again, it's the same thing. It's another linear regression. Under stat regression, we're going to do simple linear. The x variable, it says treating the, oh, well, it's labeled as x here, so I don't have to do anything thoughtful. And that's a standard output. Maximize it so I can see it. Okay, so the intercept and slope have their estimates. I'm going to take 4 decimal places this time. Okie doke. 1.2488, and we've got 0.7699. Okay. Now, assuming the residuals are normally distributed, test whether a linear relation exists between the rate of return of the index x and the rate of return of this. Okay, so is there, does a linear relationship exist? Well, the null hypothesis would be that the slope is actually 0, and the alternative would be that it's not 0. And we're testing beta 1, not beta 0. Beta 1 is for the slope, beta 0 is the intercept. We're not really, not in this course, we're not interested in the intercept. It's really the slope. Does the slope flat, or is it, slanty? The p-value is again given to us in the output. If you look over here, it was 0.0256. That rounds up to 0.026. So 0.026, which is smaller than 0.10. So we would definitely reject the null hypothesis. There is sufficient evidence to conclude that a linear relation exists. Yeah. Now let's find a 90% confidence interval for the slope. Let's go back over to StatCrunch. Now this didn't give us a confidence interval. Let's go to options. And let's create a confidence interval, a 90% confidence interval, and make this maximized. Now I've got a lower and upper bound for confidence level, a confidence interval, 4 decimal places once again. The lower limit for the slope, 0.2412, pow, and 1.2986. All right. Let's see. What is the mean rate of return for the company stock if the rate of return of the index is 3.25? Well, this is again another prediction. So let's go to edit, scroll down to, not the bottom, the middle, prediction value. If x is, what did it say, 3.25, compute. Now let's maximize that again. Scroll down, as that's where my prediction. If x was 3.25, my predicted y would be 3.751. And I want 3 decimal places, so I'm going to take all of those. 3.751. That's a prediction using the linear regression. So you could have just like gone up to that, this model rate of return of the company stock equals this plus that times x, but we can just plug it in. Cool. All right, let's go on to 26. Okay, we have a multiple regression equation. We're going to interpret it. We have y hat equals 1.77x1 plus 7.72x2 plus 33.94. That's the interpretation of the coefficient x1. It's going to go like this. If x1 decreases by 1 unit, the response will decrease by the coefficient, 1.77, if x2 was held constant. That's it. Piece of cake. Suppose there are n independent trials of an experiment with k greater than 3 mutually exclusive outcomes where pi represents the probability of observing the ith outcome. What would be the formula of an expected count in this situation? Well, okay. So you've got n is the number of trials and pi is the proportion. So it's just going to be pi times n. So for the expected number of times to say see a if p think about rolling a 6-sided die. and the probability of getting a 6 is 1 over 6, right? That's my P6. Let's say I roll the die 50 times. The expected number of 6s is 50 times 1/6. So that's the formula. That's not so hard. Okay. What are the requirements to perform a one-way ANOVA test? And is the test robust? Okay, so here's the requirements. Populations need to be normally distributed. You need to have k samples. They have to be independent in each. The independent samples, subjects in one group cannot be related to subjects in the second group, or the third group, or the fourth group. The population should have the same variance. So we're assuming equal variance for ANOVA. K simple random samples, one from each of the K groups, K treatments, yeah? And we're not assuming that variability within sample variability be less than the combined group. That's not an assumption. And we're not assuming sample means are equal. The sample means are equal is a null hypothesis, but that's not an assumption of doing the test. Okay, is it robust? It is robust. And with robustness, we're talking about small departures from normality do not significantly affect the results of the test. So anyway, that's our sample final exam. And I hope you did well, or I hope you do well, and I hope this is helpful. Let me know if you have questions, and you could put them in the comments, but, you know, or reach me another way. If you're not my student, then you can just reach out and say hi. Anyway, hope everything goes well. Bye.